Welcome to the flock. Let's dive into the concept of delta H, or enthalpy, or potential energy, and creating potential energy plots. Stick around to see how it's done. Now, before we can draw a potential energy diagram, or one of those plots I just mentioned, we have to understand where the potential energy even comes from and what that is. And how is that related to enthalpy? Enthalpy itself is a blanket term that we use to encompass both exothermic reactions. Those are the kind of reactions that release heat by forming chemical bonds. And endothermic reactions, those are the kinds that feel cold because they absorb heat by breaking chemical bonds. The term enthalpy itself is basically just saying that's a quantity, i.e. a number, a value, that's equivalent to the total heat content of a system. And this is the reason why it encompasses both the exothermic and endothermic reactions, since both of those reactions are basically saying either heat comes out of the system or heat goes into the system. And so we can say that enthalpy is the total heat energy of any system. We represent enthalpy by drawing a triangle and an H. That triangle is literally called delta, so we say delta H, and delta just means change in. Well, what does the H stand for? The H happens to stand for heat energy. So we're literally saying delta H, or enthalpy, is just the change in heat energy. We measure this change in heat energy in units of kilojoules per mole. That's very important to note. And this is the reason why enthalpy can be turned into a potential energy plot, because enthalpy and potential energy are synonymous words to each other. In other words, enthalpy is potential energy, except in terms of chemical bonds. So you likely remember from physics that potential energy is the stored energy of an object. So for its position, for example, a pen raised up higher would have greater potential energy, the potential to fall, that is, if I release it. But potential energy is also the internal capability, which is what we're more interested in here in terms of chemistry, because the internal capability of the molecule is the intramolecular bonds, i.e. the bonds holding the atoms together. So those bonds have the capability of producing energy, and that capability is literally chemical potential energy. So let's make sure that we're all on the same page here in terms of which one has greater or less potential energy. If we were to look at this coiled spring example down here, and we want to figure out which one has more potential energy, we would say, well, which one has the greater ability based off of its position or internal capability for stored energy? Hopefully you see that the one that's compressed has greater storage of energy, because if you were to release it, it would spring off into space. So here we could say that the compressed spring has greater potential energy, and the released spring has less potential energy. So then which one would you say is more stable? Which one would just maintain its shape if you were to let it go? Hopefully you understand that the uncoiled spring here would just be fine if you let it go. It wouldn't spring off into space. So that one is more stable. Whereas the one that is compressed is less stable, because if you were to release it, it would spring off. Therefore, we can draw the parallel that anytime something has more potential energy, it tends to also be less stable. Go ahead and pause the video here and make sure that you can identify in these scenarios which side has greater potential energy, which side has less potential energy, and which one is more or less stable. Ready, go! All right, these should be the answers you came up with. Notice that anytime we have potential energy at a minimum where there's less, we have something that's more stable, and anytime we have something with greater potential energy, it's less stable. Let's see what these scenarios would look like on a potential energy diagram before we move on to chemicals on the potential energy diagrams. So notice on these plots, I've drawn a Y and an X axis. I have reactants on the bottom and products on the bottom. I also have potential energy on my y-axis. Remember that potential energy is the same thing as delta H, which means enthalpy, or change in heat energy. If we consider our battery charged to be the reactant and our battery uncharged to be the product, let's graph this on a potential energy diagram. We would say that the charged battery, based off of what we determined before, has more potential energy. So I don't really care where you draw it, just draw it higher for for the reactant side because we're representing the charged battery as something that has greater potential energy on the y-axis of this plot. And the uncharged battery, the product side, would have less potential energy. So anywhere below that reactant line for the charged battery will suffice to show that it has less potential energy. Now that you've seen me draw one, go ahead and pause the video and see if you can draw the potential energy diagram for the weight on the ground as the reactant versus the weight raised as the product. Ready? Go! For this second plot, we said that the weight on the ground had less potential energy, so we would draw the line somewhere down below for the reactant side. And for the product side, we said that it had greater potential energy when the weight was raised, so it would be something higher on the potential energy y-axis. Remember that this distance is equivalent to potential energy. Now let's take this same exact concept and apply it to chemicals. We know that the potential energy is stored inside the chemical bonds between atoms. So using the same logic, we can say that if there's more potential energy between two atoms, we can say that that is a less stable bond. And if there's less potential energy between two atoms in that bond, we would say that that is a more stable chemical bond. Therefore, we can also say that if a chemical is more stable, it tends to also be a stronger bond. And stronger bonds in chemistry will always have less potential energy because they are more stable, and we could say that this minimum of potential energy is its most stable state. On the flip side, if we have a less stable intramolecular bond, that's considered a weaker bond. And weaker bonds will always have more potential energy because they're less stable. So then we can also say that when the potential energy is at a maximum up high, that's its least stable state. Okay, that's great and all, but how do we know if a bond between two atoms is going to be a strong intramolecular bond or a weak intramolecular bond? We're going to use a concept called AA versus AB bonding to try and get an idea of where we have strong or weak bonds. Now, AA and AB are just placeholders. This basically means that if I have two of the same things bonded together, like for example, O bonded to O to form an oxygen molecule, or AB to different things bonded together. For example, if I had an H bonded to an O. Now, anytime you have two same atoms bonded together, AA bonding, those bonds are weaker. And anytime you have AB bonding, i.e. two different atoms bonded together, you have stronger bonds. That means that AA bonding represents less stable bonds with greater potential energy, and AB bonding represents more stable bonds with less potential energy. So let's apply these concepts to the hot hands chemical reaction, where iron and oxygen come together to form rust, which also produces heat. Hence the reason why it's called hot hands, because it makes your hands hot. We're going to compare our reactant side to our product side. On the reactant side, we're looking for any AA or AB bonding. Here we have a metal that's by itself, iron, and we know that from metallic bonds, there's just a bunch of iron atoms all together. So that's kind of like an AA bonding situation, where it's all just the same atom present, and it's reacting with oxygen, O2. That's literally the case where an oxygen is bonded to an oxygen. So that's also an AA example. Since the reactant side has AA bonding on it, that means that it is less stable because those are weaker bonds, meaning that there is more potential energy on the reactant side. Now, if we look at the product side, we see that there's an iron bonded to an oxygen. Those are two different atoms, so this represents AB bonding. Anytime we have AB bonds, we know that those are more stable because they are stronger bonds, which means that they have less potential energy. Now, if we draw this on our enthalpy plot, i.e. our potential energy diagram, we would say that the reactants, the iron plus the oxygen, would have greater potential energy than the products. So let's just draw a line up high to represent a greater potential energy. And the products we know are AB bonding, which are stronger bonds, which are more stable, therefore have lower potential energy. We would draw a line lower than our reactants, representing a smaller potential energy. And of course, we know from the hot hands reaction that it produces heat. Therefore, since heat is released, it must be an exothermic plot. That means anytime you have the reactants higher in potential energy than the products, you're looking at an exothermic enthalpy plot. So let's just spin this another way. If the products are lower in potential energy than the reactants, then we can say that the enthalpy plot represents an exothermic reaction. What if this concept were flipped and we said that the products were actually higher in potential energy than the reactants were? In this case, we would say we have an endothermic reaction. Now remember, endothermic reactions are the ones that absorb heat by breaking bonds, and therefore they feel cold. So here's the problem you saw at the beginning of the video. Let's give it a try together. We're going to compare the reactant side to the product side and look for an AA to AB bond change. On the reactant side, we see that we have a carbon attached to a hydrogen. Those are two different atom types, so that's AB bonding. We also have O2, that's two oxygen atoms bonded together. That's representing AA bonding. How about the CO2 on the product side? That's a carbon attached to an oxygen. Those are two different atoms, so this is AB bonding. And the water, the H, is connected to O. This is also AB bonding, two different atom types. So since the reactant side has AA bonds present, remember those are weaker bonds, therefore they're less stable and have greater potential energy. And the product side only has AB bonds, those are stronger bonds, and since they're stronger bonds, that means they are more stable, meaning that they have less potential energy. So let's draw this concept on our enthalpy diagram. The reactants are our C3H8 plus O2, and we said that they had greater potential energy, so we're just going to draw the line up higher. On the product side, we have CO2 plus water, and we said that those products had less potential energy, so we'll draw the line down lower. Just as we saw before, anytime the reactants are greater in potential energy than the products, we have a potential energy plot that's representing an exothermic reaction. The way I remember that this is an exothermic reaction is that I think of the letter X, and I draw an X like this between the reactant and product lines. Now that you've seen me do it, go ahead and pause the video here and see if you can draw the potential energy enthalpy plot for this chemical reaction. Ready? Go! Ready to check your answer? Let's do this. Hopefully you found that the answer is that this reaction is endothermic because the reactants are lower in potential energy than the products. An easy way that you can remember that this type of graph represents an endothermic reaction is that you can draw an N between the reactant and product without lifting your pen and connect both of those lines. N like endothermic. In summary, we know that exothermic reactions release heat. They feel hot. The reactants are always going to be higher than the products on the enthalpy plot. And that means that the potential energy from the chemical bonds intramolecularly is literally converted into heat. We feel that as heat. And an endothermic reaction is one that takes in heat energy. That means that it feels cold to the touch. This is because the heat energy put into the system is converted into potential energy in the chemical bonds. And on an enthalpy plot, we're always going to have the reactants lower in potential energy than the products. Remember that a really easy way to determine the difference if you're just looking at the graph is that you can draw an X between the lines for exothermic, or you could draw a complete N without lifting your pen from reactants to products for endothermic. As always, make sure you test yourself before you wreck yourself, and make sure that you can draw an enthalpy plot for both the exothermic and endothermic enthalpies from memory and determine if the products would be more stable, less stable, stronger or weaker bonds, more or less potential energy. Remember that AA bonds represent chemicals that have weaker bonds, and if they're weaker, that means they are less stable, and if they're less stable, they have greater potential energy. Whereas AB bonding is a way to determine if something has stronger intramolecular bonds, and if it's stronger, that means it's more stable, meaning that the potential energy would have to be less. Please give this video a quacks up, and I hope that helped you understand enthalpy and enthalpy plots a little bit better, and please subscribe to the Duckonta channel for some more free educational content. Be sure to keep your life just quacky. See you next time.
No ducks, no glory.